Hello, my name is Dr. Steele, and welcome to Steele Mathematics, where lessons in Algebra 1, Geometry, Algebra 2, Pre-Calculus, and Calculus are taught. And today, we are going to talk about finding the roots of polynomials equations of degree higher than 2. Now, I want to make 3 points before actually going into it. And the first point is that a polynomial equation of degree n has n roots. For example, a polynomial equation of degree 3 has 3 roots, or a polynomial equation of degree 7 has 7 roots. The second point I want to make is the fundamental theorem of algebra. A polynomial equation of degree n has at most n rational roots. Now, I just said that a polynomial equation of degree n has n roots. And at most n of them can be rational roots. For example, let's say you have a polynomial of degree 4. That means it has 4 roots. Well, 2 of those roots can be rational, or 3 of these roots can be rational, which means the rest of the roots can be irrational or complex. That's what the fundamental theorem of algebra is saying. Then we have the rational root theorem. If a is the leading coefficient and c is the constant term of a polynomial equation, then a possible rational, and that's supposed to say rational, root is a factor of c over a factor of a. So now, how do we find the roots of a polynomial equation? Well, we use the rational root theorem to list all possible rational roots. Then we use synthetic division to determine which possible rational roots are actual roots. Now, let's take a look at some examples. Let's say you are to find the roots of the following. Well, the degree is 3. Therefore, this equation has 3 actual roots. So to find out what they are, well, we're going to list our possible rational roots. A is 1 and c is 36. We're going to list the factors of 36. Let me erase it. 36. We got positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 4, positive and negative 6, positive negative 9, positive negative 12, positive negative 18, and positive and negative 36. So these are all the factors of 36. Next, we're going to list all our factors of 1, which is just positive negative 1. Now, it's very important that you list both positive and negatives when you're listing your possible rational roots. Therefore, your possible rational roots are 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, 4 over 1, which is 4, 6 over 1, which is 6, 9 over 1, which is 9, 12 over 1, which is 12, 18 over 1, which is 18, and 36 over 1, which is 36. So these are all our possible rational roots. And the fundamental theorem of algebra says that at most 3 of these are actual roots. Well, let's see which ones. We're going to use synthetic division. So this is 1, 1, negative 24, 36. Draw a line, draw our remainder box. So now we're going to see which number we're going to try first. Let's try 3. Bring down your 1. 1 times 3 is 3. 1 plus 3 is 4. 3 times 4 is 12. Negative 24 plus 12 is negative 12. And 3 times negative 12 is negative 36. 36 plus negative 36 is 0. Okay. If the remainder is 0, that means 3 is an actual root. So we have the first of 3 roots. So now we got to find the other 2 roots. But here we have 3 numbers. When you have 3 numbers, that means to find the other 2 roots, you just solve x squared plus 4x minus 12 equals 0. By the way, the 0 is not the 0 that's in the remainder box. But we're setting it equal to 0 to find the other 2 roots. And we're going to solve this by factoring. So you draw your 2 sets of parentheses. You're going to make a big X. You know, x times x is x squared. 1, the leading coefficient, times negative 12 is negative 12. And the linear coefficient is 4. So we're looking for 2 numbers that you multiply to get negative 4 and add to get, multiply to get negative 12 and add to get 4. And those 2 numbers are 6 and negative 2. So this is x plus 6, x minus 2. Now we're going to set each factor equal to 0. Subtract 6 from both sides, you get x equal negative 6. So negative 6 is your second root. And we're going to solve x minus 2 equals 0 by adding 2 to both sides. You have x equal 2. And therefore, there are your 3 roots. Next, you actually find the zeros of the following. We got f of x equal 3x to the 4th minus 26x squared minus 13x plus 30. So the first thing we're going to do, we're going to list our, okay, first of all, before we even do that, the degree is 4. Therefore, this is going to have 4 zeros. So what we're going to do is we're going to list our possible rational zeros. You know, A is 3 and B, C is 30. Next, we're going to find all our factors of 30. Positive negative 1, positive negative 2, positive negative 3, positive negative 5, positive negative 6, positive negative 10, positive negative 15, and positive negative 30. Next, we're going to list our factors of 3. So we get positive negative 1 and positive negative 3. So now we're going to list our possible rational zeros. 1 over 1 is 1. 2 over 1 is 2. 3 over 1 is 3. 5 over 1 is 5. 6 over 1 is 6. 10 over 1 is 10. 15 over 1 is 15. 30 over 1 is 30. Next, we're going to go 1 over 3, 2 over 3, 3 over 3 is 1, and we got that already. 5 over 3, 6 over 3, which is 2, 10 over 3, and 30 over 3, which is 10. So these are all our possible rational zeros. So now we're going to use synthetic division. We got 3. We don't have an x to the third. That means its coefficient is 0. Negative 26, negative 13, positive 30. Draw our line. Draw our remainder box. So now the first thing we're going to do, we're going to try 5. Bring down your 3. 5 times 3 is 15. 0 plus 15 is 15. 5 times 15 is 75. Negative 26 plus 75 is 49. 5 times 49 is 245. Negative 13 plus 245 is 232. 5 times 232 is 5. And 30 plus 1,160 is 1,190. So as you can see, the remainder is not 0. Therefore, 5 is not an actual root. So we're going to try another number. Let's try 3. Bring down your 3. 3 times 3 is 9. 0 plus 9 is 9. 3 times 9 is 27. Negative 26 plus 27 is 1. 3 times 1 is 3. Negative 13 plus 3 is negative 10. And 3 times negative 10 is negative 30. And 30 plus negative 30 is 0. So as you can see, the remainder is 0. Therefore, 3 is one of your 4 actual roots. Now, as you can see here, we have 4 numbers. That means you're going to have to draw a half box next to this and draw your remainder box underneath 10. And we're going to try 2. Bring down your 3. 2 times 3 is 6. 9 plus 6 is 15. 2 times 15 is 30. 1 plus 30 is 31. And 2 times 31 is 62. Negative 10 plus 62 is 52. So as you can see, the remainder is not 0. Therefore, 2 is not an actual root. So now, we're going to try negative 2. Bring down your 3. Negative 2 times 3 is negative 6. 9 plus negative 6 is 3. Negative 2 times 3 is negative 6. 1 plus negative 6 is negative 5. Negative 2 times negative 5 is 10. Negative 10 plus 10 is 0. So negative 2 is an actual 0. And I meant to say 0 last time instead of roots. So now we got 2 more zeros we have to find. But look, there are 3 numbers here. That means we can solve the quadratic equation 3x squared plus 3x minus 5 equal 0 to find the 2 other roots. But it seems like 3x squared plus 3x minus 5 cannot be factored. Therefore, we're going to use the quadratic formula. So a is 3, b is 3, and c is negative 5. X equal negative 3 plus or minus 3 squared minus 4 times 3 times negative 5. All over 2 times 3. All right, we're going to go ahead and find our discriminant. 3 squared minus 4 times 3 times negative 5. That gives you 69. And 2 times 3 is 6. So our final 2 roots are negative 3 plus or minus the square root of 69 over 6. And there you have it. Our 4 zeros. And again, sometimes, when you're looking for zeros, sometimes I might be in the habit of saying roots. But there are 4 zeros. Let's do one more example. Let's say you ask to find the zeros of the following. Well, we know this function is of degree 3, so there are 3 zeros. It has 3 zeros. So the first thing we're going to do, we're going to list all our possible zeros. A is 1. C is 21. We're going to list our factors of 21. So we got positive negative 1, positive negative 3, positive negative 7, and positive negative 21. Then we have 1, and the only factor is 1. Therefore, our possible rational zeros are positive negative 1, positive negative 3, positive negative 7, and positive negative 21. So now we'll list our possible rational zeros. That means at most 3 of these are actual zeros. So we're going to use synthetic division to see which one of those zeros are the actual ones. So we got 1. There is no x squared, therefore its coefficient is 0, -2, and 21. So first we'll try 3. Bring down your 1. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. -2 plus 9 is 7. 3 times 7 is 21. 21 plus 21 is 42. So as you can see, the remainder is not 0. So 3 is not an actual 0. So we're going to try -3. Let's try -3. Bring down your 1. -3 times 1 is -3. 0 plus -3 is -3. -3 times -3 is 9. -2 plus 9 is 7. -3 times 7 is -21. And 21 plus -21 is 0. So as you can see, the remainder is 0. Therefore, -3 is the first of 3 zeros. Now we got to find the other 2 zeros. The good news is there are 3 numbers here. That means we could use the equation x squared minus 3x plus 7 equals 0 to find the other 2 zeros. And it looks like we're going to have to use the quadratic equation because we can't factor x squared minus 3x plus 7. So a equal 1, b equal -3, and c equals 7. So now we're going to set this up. -3 is +3, plus or minus the square root of -3 squared minus 4 times 1 times 7 over 2 times 1. We're going to go ahead and do our calculations. We're going to find our discriminant. So we have 3 squared minus 4 times 1 times 7. That gives you -19. 2 times 1 is 2. The square root of -19 is I times the square root of 19 over 2. Now we're going to write this as 2 complex numbers. Therefore, this would be 3 over 2 plus or minus the square root of 19 over 2i. And there are our remaining 2 zeros. Therefore, our 3 zeros are -3, 3 over 2 plus or minus the square root of 19 over 2i. To find the roots of any polynomial equation, you must first understand how many roots it's going to have. And to find out what the degree is. Once you find out how many roots it's going to have, then you're going to list all your possible rational roots. Finally, you're going to use synthetic division to find out which of those rational roots are actual roots. I hope that you have a wonderful and blessed day.